Good evening, everyone. Welcome to WeWork at 2 Embarcadero Center, hosting Tech Week this week. This brings us to our fourth day, our sixth event of the week. It's been amazing seeing the foot traffic in the city, the community coming together. We've had roughly 5,000 people flow in and out of our space this week. It's been awesome just bringing the community together. We've opened our doors this year to ensure that we provide spaces where we can inspire and help propel our tech communities work forward, and it's been amazing seeing the reception. Tonight we have something really special planned, harnessing AI and relational data. Thank you to our hosts, MotherDuck and Ryan. Thank you for bringing us together, sponsoring this event. My name is Ashkan. I oversee our partnerships and sales team here at WeWork. Been with the company for coming up on roughly 7 years. We've had quite the journey ourselves, but just want to say a quick thank you for everyone coming out. I'll kick it off with our first speaker, Madelon with CWI. We're really excited for the content tonight. Hope you guys enjoy it. Thank you.
All right, welcome everyone. I think you said it all, but great to see you all here. I'm very excited about talking today, especially for the industry audience that we have here as well. So we really are keen to bring research and industry closer together, which I think is very important for specifically this topic. What I'm going to talk about today is retrieval systems for structured data. I'm coming from the research side, so I'm a researcher at CWI. But I think there's many applications in industry, and where I think retrieval is really a missing piece currently for coupling, for example, LLM-powered query interfaces to also get insights from structured data, which contains factual data typically. So let's start. Why I think it's important? Well, finding the right data, which can be for simple questions, but also for deeper analysis, is simply not easy. And today, I'm going to talk about two projects that I've been doing as a researcher at Berkeley, along with the EPIC Lab. I'm first going to talk about how to help data analysts to find the right data for ML use cases or data analytics use cases. And second, I'm going to talk about another retrieval use case where we try to really ground LLM-powered query interfaces in structured data. And I think you'll see the difference as we go. Maybe before I continue, I realize I didn't really announce the full program, but just to go over that. After me, Till will give a talk, Laurel from MotherDuck and Number Station, and then we'll have a break from 7 to 7:30, where we also have food, which is on the right side. Sorry, I forgot, I skipped this part. I also was supposed to mention that we have bathrooms in the hall over there. So I think that's in terms of logistics that I skipped. After the break at 7:30, we'll have a great talk from Jure from Stanford, but also who's also with Kumo AI. And we'll finish with a very exciting panel, which will be joined also with Shreya and Bryan from Berkeley and Hex. And there, it would be really nice also to hear your questions and hear your experiences perhaps, so feel free to chime in then. All right, and now I'm gonna really talk about this. So in two parts. Part one, how to help data analysts find their data for data analytics tasks. So before becoming a researcher, I was actually a data scientist myself, and I really found it always very hard to find a particular data set. It didn't take hours, it really took weeks to find the right data set for a given task. Because imagine that you're looking for a data set to forecast, for example, monthly energy consumption per household until May 2025. Well, you might have internal databases, you might have multiple different data sources from different cloud data warehouses or whatever, or you might figure out some data that you can find on the web, for example, through Google Dataset Search. And then, you need to figure out as a data analyst, what it can actually be used for this specific task. So what you can do is, here you have these typical interfaces, here giving access to like public data, but this is also for private data, a very similar interface. So you go to Google Dataset Search, you type in your like keywords there, and maybe you have some additional filters. What you end up with is typically many data sets. Here, actually, for this query, which is pretty well defined, you have around 70 data sets, but it's really hard to figure out which one is actually the right data set for a particular use case. And while this is only 70 data sets, very often you get search results of like thousands of data sets with just a few keywords. So the question is, how can we make that better, and why is it actually still so hard? So we asked data practitioners about this, very diverse set of practitioners across different positions and industries. And we asked them, like, how do you actually search? And it turns out that they all rely on consultations with coworkers. And this might resonate with you as well if you're looking for a data set. But people try to identify other people who've been working on similar problems and then take it from there. Because the problem is that no one really knows what data is available, no one really knows what data can be used to a given task, and that's just really, I think, the main problem why it takes so long. But then, why this is also the case is, of course, that existing systems are not flexible enough. So, so that's one of the issues. But I think the biggest issue that we've seen here is that typically relational databases and the data that is stored in there is not really like descriptive. So, for example, the variable names are really messy, they are inconsistent across different tables, or they're just really hard to understand. But also the categorical level of like the detailing of the granularity is also really unclear from looking at this data. And there are some other issues that I think it's really time to really solve this. And we're also in an exciting era, of course, with LLMs, for example, and embeddings, etc., to start doing that. So we've been thinking about how can we get to next generation dataset search systems, and we came up with a few requirements to tackle this. And I think first, systems should, instead of being data descriptive, where you need to kind of type in keywords, they should instead be task-driven. So you just want to say, hey, I want to train a model for whatever forecasting task. And that's how you want to search. You don't want to describe your data, because no one really knows what data you actually need. Second is that search should be really hybrid. So you want to search over metadata and do that in a flexible way. But you also want to search with semantics. And I think with embeddings, we're now in the position to do that. And then I think search should really be way more iterative. It cannot just be a search bar with a few filters. It should be really, really more iterative. And I think there, again, we have like great tools now with conversational interfaces, for example, to break queries down. Then the last requirement, I think, is that search results should be way more like easier to understand and to digest. So it should be way easier to differentiate one data set from another, for example. So we have a few ideas of how we can overcome some of these challenges. And one is towards task-driven search. And there we are really experimenting with hypothetical schema embeddings. Because the problem is your task does not align well with the semantics of your data sets. So here, if you imagine this task-driven query about training a machine learning model to forecast demand for medicines across suppliers, that's the task that you want to accomplish. What you can do, you can take this task, generate a hypothetical schema, so perhaps a few tables that you can use to address this task, so to implement this forecasting model. So you can use, of course, an LLM, a large language model, to generate such a schema for you, and then use that to retrieve over your data sources. So what you do, you embed your hypothetical schema and then retrieve tables from your data source that are similar to this schema. Fairly easy approach, I would say. So we're figuring out how that is effective. Then another important requirement here is to really do this iteratively. And I think, as I said already, with conversational interfaces, you can actually do that. So, you really want to break it down into, small components. So this is, on top you see an example query that one of the practitioners provided to us. And the actual requirements of a data set, like the needs of a data set, is way more complex than what fits into like a keyword search box, for example. So you really want to be able to specify the full search need of these data sets. And then you can break it down. So I want to have a data set for task X. The data should contain ABC, like certain columns, for example. It should span 2 years, so that's like metadata attributes, and with a certain date range, for example. And then, you have, for example, granularity, so you need to also extract granularities from the underlying data sets. And there can be also more like basic metadata attributes, like the number of records in a table. So here we start with like these hypothetical schema embeddings, and we go down, pruning the search space, ending up querying the metadata part. So this is the hybrid component, the hybrid search approach, through text to SQL. So we basically take, these text specifications, turn it into a SQL statement, and then execute that. And this is, I think, what we're currently working with, and it's quite effective so far, but of course it also needs an interface, so that's something that we're focusing on now. And here I think it's really important to really help a data analyst to search through their data sets. And we're figuring out how we can proactively guide data analysts in their search. So yeah, this is a current interface that we're looking into. But this is like early work, so this requires some user studies also to figure out if it's effective or not. So this is, I think, the first part, data discovery. Data discovery is quite a hard challenge, so definitely worth looking into, I think. And there are some startups on that, but it's definitely something, that should be improved, I think. And it's a good era, like a good time also to do so. Then I want to switch to the second part, because retrieval, and a great use case of a retrieval, of course, is also to empower like LLM interfaces and ground them in structured data. And here I want to start with an example question that you might ask to an LLM. So you might have like very easy questions that you can just easily ask an LLM, and an LLM has that in memory. But imagine that you're wondering, maybe as a parent, like what is the highest eligible free rate for K-12 students in the schools in Alameda country? Well, I'm from the Netherlands, so this is not really familiar to me, but hey, ChatGPT can contextualize this question. It knows what it is about. But here, it gives this answer. Actually, there's like way more context and elaboration from ChatGPT around this, but I wanted to focus on this specific part of the answer. To determine the highest free rate, specifically in Alameda County schools, you generally need data from specific school districts or schools in the area, as this rate can vary widely depending on socioeconomic demographics of each district. And I think that's really true, and we have a good paradigm now that we can use to get this specific data. Retrieval augmented generation, or RAG, you probably heard from that. What we do there is we just connect an LLM with an external data source, which can be knowledge bases or text corpora, etc. Images, video, that has been explored. But the question is, can we really answer this question best while connecting it to these data sources? And I think there are better data sources to connect it to. surprisingly, relational data. So I think this is an exciting time, and it's very timely to start working on RAG for structured data and see how we can perhaps more efficiently enrich LLMs with the right data sources. So here we can really explore relational databases as a source for RAG. And then you will see that you will actually find the right answer, if connected, of course, with the right databases. So why do we need RAG over structured data? Well, I think a pattern that I've seen in generative AI research is that no one really cares about structured data. But as you probably know here, and that's why you're here, of course, is that in practice, everyone really cares about structured data. Because structured data is all around, actually, in like the enterprise data landscape. Because structured data really serves high-value insights. Because structured data typically is up-to-date, it has domain-specific knowledge, and it typically contains facts. So let's look into a few examples of queries. I think we're a little bit short on time, but you can imagine that you might have like fact verification queries, you might have more aggregation queries, or just like simple table lookups. And then you can enrich these kind of questions with structured data. So what does such a pipeline look like? Well, first you start with your question, you contextualize your query, do some interpretation, then you have your retrieval component, and then you do some generation on top of that, which can be just a table lookup and let the LLM interpret the table, but this can also be generating a SQL statement to execute on top of your relational database. And then finally, of course, you get your response. And there has been lots of research and work and like startups focused on how to contextualize and maybe enrich these queries, as well as how we can generate proper SQL code for given questions. But the question is, how do we actually retrieve structured data? And also given the different tasks that we can perform, it's really hard to understand how we should route through all the tasks that we might be doing. So here I really want to stress that the retrieval component here is really difficult to do well, but it's really crucial. Because as Wen-Hu nicely said, he's a professor at the University of Waterloo. Keep in mind that a good RAG system is really hard to build, but if your retrieval system is mediocre, and I think most people here will agree with that, the retrieval can easily distract LLMs to backfire. And really in the kind of context of structured data, there's really a long way to go. This has not really been studied in much depth. So there are important grounds to explore here, and how kind of complex your retrieval and generation is really depends on the query, and we need to kind of understand queries there. So what does this kind of task, what does the query try to do, for example? But there are many other questions underlying here. So how should we process a table? What should we actually embed from a table? Should we embed also metadata, or does it only instruct the embeddings? Given the query and embedded corpus, how can we actually retrieve then the relevant table? Which data sources to retrieve from? Should we and can we generalize across data sets and tasks? And so on. And there are many, many other questions that have not been explored. So here at Berkeley, we've now introduced a new benchmark for this task we call Target, so benchmarking table retrieval for generative tasks. And Target actually incorporates like the different tasks now that we have over structured data. So that can be like question answering, fact verification, text to SQL, and we integrated like the common data sets here. I must note that Target is still in development. Tsinyu here, who has been working on this also, definitely chat with him afterwards, has been, we're still collecting new data sets and tasks here. So I'm gonna skip through a little bit of this, but we have like retrievers, like common retrievers, like BM25, as you see also for unstructured data, commonly used. We have like Llama Index has a out-of-the-box retriever there, as well as very like straightforward, naive embeddings with OpenAI models. So those are the retrievers that we've been evaluating. Those retrievers return like top K tables, hopefully also with the ground truth target table. And then we have like very basic generation functions, but those can be advanced as well. And we've been really focused on building a diverse benchmark, which we're now expanding on as well. But it should also be extensible, so you can just evaluate any custom retriever as you see fit. I want to focus now a little bit on the insights that we got from targets that I think will be useful also when you want to implement retrieval for structured data. And there's particularly one point that I want to stress here, because I know that for like text documents, people say that BM25 is quite a robust choice for a representation, and BM25 is like a sparse lexical representation of your data. But for structured data, and this might be very obvious, but for structured data, this really doesn't work. So the retrieval performance here is much, much lower if you compare it, for example, to the retrieval performance of Llama Index or like more other dense embeddings, such as with OpenAI and very like naive embeddings there. So definitely don't use BM25. If you want to take anything from that, then this is the conclusion. Another thing that we are looking into, like what should we actually embed here? And one thing that we found is that if you embed like rows, can be like a sample of rows 10 or 100, this can actually distract your embeddings from the real semantics that actually matches with the kind of input queries. So definitely think about or evaluate whether, what kind of inputs for your embeddings make sense in terms of the queries that you hope to serve. And especially in like relational databases, we've seen that just adding like numbers, which we typically see in relational databases, just doesn't provide any semantic context for these embeddings. The Llama index retriever generates a summary and from a table and then embeds that to the retrieval. But here we find that not all tables apparently are easily summarized. So this is something, to evaluate on first as well. So I think the key insight is that there is much to do still in this area, and we need better retrievers. But it's also not a kind of single solution that works for all these data sets and tasks. Yeah, then I want to quickly jump to the conclusion, but you can use Target for evaluating your retrievers. But yeah, to summarize the key takeaways, I think retrieval is really critical to get insights from data, whether it's data discovery or retrieval augmented generation to empower LLM interfaces for structured data. We've introduced a few methods that we're currently exploring, but yeah, I owe you some better evaluations on that. But I think there's promise in like hypothetical schema embeddings, for example, to do a very lightweight retrieval for data discovery, but also for retrieval augmented generation, for example. We introduced the first benchmark for RAG for structured data, and I hope that can help us to build better retrievers for structured data. And there's more to come on that. So yeah, that's it. Please reach out to me, Madelon at Berkeley or Madelon at CWI, if you want to chat about this, or if you have any experience from industry, because I would love to hear if you have any like approaches that work better for you. And with that, I want to hand over to Till.
All right. Good. Sorry, that was loud. So my name is Till, and I'm running the machine learning team at MotherDuck, together with Aditya, who is also somewhere in the room. There he is. All right. And I'm going to talk about small language models for small data. So, and first I'm going to talk about small data. So, what is small data about? 2 weeks ago, or 3 weeks ago, we had this conference called Small Data Conference. And yeah, it's all about the opposite of big data. And that is kind of motivated by a couple of observations. And It starts with most people actually don't have that much data. When we talk about big data systems, maybe there's a good chunk of people that actually have not so big data and don't need these kind of systems. Another one is, even if you have a large amount of data, it might be, a good fraction of that data might be historical data. And the data you analyze, you know, in your weekly reports and so on is actually only a small fraction of that. And the other one, even if you run larger workloads, you might have filters in there and so on and so forth. And so actually, most of the time you don't really need a big data system. And that observation is backed up also by data. There was the Redshift data set published a couple of weeks ago that contains metadata from query workloads on Redshift. And it actually turns out that only one out of 500 users would actually qualify as processing big data. And the thing is, how can we build systems for small data, and how can we leverage the fact that people don't have big data? And one way to do that is to say, okay, you have actually compute power locally, and single node compute in the cloud is actually really, really powerful. So you have compute nodes with up to 24 terabyte of memory and a lot of cores. So you can do a lot with single node compute and actually save all the overhead that comes with distributing workloads. And so that's where DuckDB basically comes into the picture, because DuckDB is an extremely efficient analytical database system. And on the left you see the benchmark of it. It is orders of magnitude faster than pandas, for example, and it's a single node database, and it's actually becoming really popular with people because they feel, okay, I have this 20 gigabyte file locally, and I don't need to upload that to some cloud data warehouse. I can actually just process it on my notebook, and it's even super fast. And so the other story is then, what does MotherDuck do then? Because MotherDuck is not DuckDB, and so we as MotherDuck, we basically give DuckDB a cloud companion. So we give DuckDB a second DuckDB that is sitting in the cloud. Because you might be running workloads locally and at some point hit a bottleneck still. But then we can give you a second worker in the node, in the cloud, that now can leverage single node compute on large servers, and can take away a big chunk of the work for you. And the benefit that comes with that is it brings data sharing, for example, into the picture, because as soon as your data is also in a cloud, you can share data sets with other users in your organization and so on. Same with notebooks. So basically, brings DuckDB to an enterprise level. So now I want to start talking about small language models and how they fit into the small data world. And this is all motivated by the developments in the recent years. 4 years ago, when GPT-3 was released, 1 million token cost around $20. Now GPT-4o is at $4 per million tokens. But then there are also smaller language models, like GPT-4o Mini or Llama models, other open models that are much cheaper to run. So we're talking about 99.7 lower cost. And actually, compared to the original GPT-3, those super G models are even better than the large GPT-3 model. So why are we talking about this in the context of databases? It's because a lot of data in database data warehouses is actually are actually strings. So 50% roughly. There are different studies on that. Like one of the left side is actually from the Redshift paper. So 50% of columns are varchar columns, and so they're kind of locked up for data analysts to a certain extent, because okay, what kind of tools do we have in databases to deal with strings? We might have like a regular expression extraction function and so on, but I mean, ideally we would just leverage language models to help us with our analytical task on these textual columns. And these pre-trained language models or small language models are actually like very multifunctional tools. I mean, there are a lot of specialized models or specialized approaches for all these different problems, but they're usually very hard to actually use. For some of those things, you might actually need to have training data. For others, you might need to write a UDF, and you might need to deploy a specialized sentiment classification model somewhere, and so on and so forth. And that just makes it adds much more friction to the analytics process. So, and one thing we did recently was to add a new function to MotherDuck that actually lets you call language models in SQL. And like one thing you can then do with that function is, for example, this is a review data set, so there are product reviews in there, and they're a bit hard to read. So what you can do, you can actually say, hey, okay, just add a new column with a summary of that review. And here's a bit bigger picture of the query. So yeah, it's just a scalar function, and it will run all your rows against a small language model. And what I think is really cool is the structured output. So now language models can actually return JSON files and also adhere to the JSON schema that we give those models. So we can actually generate structs or JSON based on an instruction and incorporate that into our analysis. So here I have this review text, and I just say, okay, return a struct that actually contains 3 different fields. One is the summary, but also I want to have 2 lists of positive and negative aspects that were mentioned in the summary. And I want to get a rating. Like, I don't have a rating column in my data. I want you to infer a rating from based on the review that the user wrote. And yeah, so in the end I end up with that data for each entry in my database. And yeah, maybe to take a short break. So I think, of course, you can do that with ChatGPT or with a Python wrapper and do all this. But the convenience of being able to do this in SQL is it's just really nice. And there's also an embedding function, so you can embed tags, and then you can do things like similarity search and answer questions like this one. So here we have we've seen a review from a user, and it just said we didn't think it worked well at all, and we don't really know what to infer from that. So what we do then, we just look for for similar reviews for the same product and see if we can maybe get some information from those. And actually there we can find different reviews that contain the information that this product is probably some kind of sticker that it didn't stick well. So that's a really nice insight that probably would have taken super long to get from just reading the different reviews. And yeah, okay, to come to the next point. So, I mean, what we are, right now this prompt function is talking to OpenAI, doing inference with GPT-4 Mini. But as I said before, in this execution model of MotherDuck, we actually have two components. We have the local compute and we have the cloud compute. And they actually both share the workload. So when you execute a query in MotherDuck, part of your query will be executed locally and another part will be executed remotely. And the two workers coordinate the work in a way that they minimize network traffic and optimize for speed of the query execution. And but another aspect of that is you can actually leverage also your own compute for doing this kind of inferences. And I think that's an interesting topic because there are a lot of open models out there and local inference is on the rise. There are things like Ollama or VLLM that make local on-device inference quite easy. And yeah, that's kind of the vision. And MotherDuck is just a really nice interface that then unifies local and remote language model inference. Okay, so as I mentioned, there are a lot of specialized methods actually already out there to do NLP tasks. And these language models are basically a big hammer. They can do everything, but they might not be the right tool for every task. So I want to go through a couple of papers or a little bit of research. Like this work has actually been done by the next speaker, or at least you were involved in that. Yeah. So that's about data wrangling with language models, and I think that's the most interesting aspect of having these prompting capabilities in the database, because you can not only use them to do NLP for analytics, but you can also leverage them to clean your data, to transform your data, and so on and so forth. And this work shows that doing that with large language models is actually quite working relatively well for certain tasks. And then we've done some follow-up work where we fine-tuned smaller models, really small models. T5 has only 220 million parameters, which is a fraction of the size of GPT. And I think I have another slide where I also show the difference that it makes for inference time, which is of course like a concern when running a couple of thousand or 100,000 rows through a language model. And these models are actually provide a quite okay inference time for that. And but then you can go even further and say, okay, what if we could just generate SQL code that is doing what we want to do? Because there are some cases, some data sets in these benchmarks, for example, that are about unit conversion. So I have a column, there are numeric values in there, or like let's say it's a column with meters. So I want to convert that column to feet. And I mean, I could Google the formula for the function conversion, but ideally, or it would be more convenient to just write a prompt essentially that says, hey, convert this unit from X to Z, and then my text to SQL model essentially spits out the right formula for that. And that works well specifically for those transformation tasks. That's something that came out of this. And yeah, here's a slide with the inference time again. I just what I want to say. Okay, you can use this prompt function to do a lot of different things. Maybe like unit conversion is not great, not a great example for that. But in the end, if you can do it in SQL or with some kind of SQL function, it's probably the best for you. But there's nevertheless things like text summarization, for example, that a regex function will never be able to deliver. And so I guess that's kind of the conclusion of that. We need different tools for data wrangling, and they have different trade-offs. And we kind of have to live with that, and have to figure out a way to a principled way to to choose the right tools for the right task. And yeah, that's it. Thank you. Why does it work with with large language models? And
framework, all that, right? So that works for the LLMs.
Mm-hmm.
So exact same thing works for small language models.
Mm-hmm. Okay, yeah. So the question is basically, if I understood correctly, if like the same thing that works with large language models like GPT-4, does it also work with the small language models? Like, can I prompt it? And okay, so I would say, like, there's still two different categories of small language models, like the pre-trained one that are optimized, that have the instruction fine-tuning part, and I think that goes a little bit into the why direction. I mean, they're trained super long. I think that's what makes the models, the smaller language models nowadays, so good, because they're trained on an insane amount of data, and for a really long time compared to the small language models from a few years ago. But the smaller the models get, the more they go into a territory where you actually need to start fine-tuning. So at that point, you actually need either use case specific training data, or you need to pick a model that has been fine-tuned for a specific task, like sentiment classification, for example.
If your small data includes like audio files, docs, or images, does your technique still hold in terms of whatever you talked about?
Yeah, so the models we have integrated with are text models. So DuckDB itself can store blobs, for example. So you know, there's a world where you could store images and have essentially the same function, and just pick a different model that can actually interpret the blob in that column and do something similar.
My understanding was that I needed a big set of data so the model know everything, so it can predict. And if you have a small amount of data, how can the model project on something that it was never trained on?
Mm-hmm. Yeah, that's an interesting question. I think that's the main benefit of using these pre-trained models, because they are already trained, and they don't need to be tailored to one specific data set. So the data set could be like just one row, and it would still...
So my understanding is you have a big model, and the small model is another more specific for the user, and that's the small model. But you still use a big model, correct?
I'm not sure I'm understanding.
When you are talking about pre-trained model,
Mm-hmm.
the pre-trained model is big or is small?
they exist in different sizes, and I would say there are some that fall into the small category. Like I think no one decided when the small model category started, but I would say it's around like 8 billion parameters and below, and I think up to 1 billion or 350 million parameters you can find, pre-trained models. That kind. I guess we have to
Okay, so hi everyone. My name is Laurel Orr. I am the ML architect at NumberStation, and we basically are applying Gen AI to the data stack. And in particular, going to talk to you now about some kind of new stuff that we're doing, really diving into structured data agents backed by LLMs, and really how those are going to be able to. Our hypothesis is to be able to automate a lot of these like structured data workflows. So the talks can kind of be in 3 parts, although the last 2 are sort of into this like technical deep dive. I'm kind of going to give you guys my somewhat biased opinion on what the structured data stack actually looks like today, and then talk a little bit in more of a technical depth about how we're kind of addressing this with what a structured data agent looks like and why it's beneficial, and then kind of moving into the new frontier of these kind of multi-agent platforms that have been kind of on the rise over the last couple of years. So for people who've been in the space, the modern data stack has a lot more questions than they have answers. If you've ever worked on a data team, they are typically inundated with questions from business analysts trying to understand their data, right? They have questions around what table should I look at, what my schema is, can you create new dashboards for me? Where even is this dashboard, right? Those Slack channels that we look like, that we have been working with, and it's just there's a ton of questions, and the teams are really struggling to keep up and answer all these questions on time, because it takes 1 second to ask a question and usually multiple days, if not weeks, to answer them. And this has also been harder because even with AI, a lot of these promises have been made that these problems are going to be solved, right? Self-service BI is coming, and Gen AI is going to empower the stack, and everyone's excited about all these tools. And in reality, kind of nothing is really solving the problem, right? 44% of companies say that their teams are providing value. Their data teams are providing value, which means that 66% of them are not. Right, and so let's actually look at a high level about what the data stack kind of looks like today, right? And so you have all these kind of varies, you have models that are being used, usually backed by some clouds, and you have a giant pool of different data sources, right? And these I'm considering beyond just classical relational databases, which are of course on there, but really where is your structured data living throughout your entire enterprise, right? It's living in Power BI tool, like dashboarding tools, right? It's living in your Slack channels. You're messaging and talking about the structured data at the same time. It's in all your documentation, like DBT workflows. It's in your DuckDB files. So they're really everywhere, right? It's all over the place. And so what you'll have is that different companies kind of pick and choose different tools and different systems and glue them all together in these maddening pipelines. You'll have companies that take their data from Redshift and move it to Snowflake and then put it back in, Databricks, and they have 3 different, dashboarding tools that all look at different segments of the data, and no one knows where anything is, and it's kind of just maddening. And at the end of the day, you have this data team who is like fighting the good fight, trying to provide answers to these business users. And this is just a very painful world to live in. You have these very idiosyncratic sort of data pipelines that are kind of picking and choosing all of these sort of BI analytics tools. And these tools have been augmented with Gen AI data, right? A lot of them have been kind of this like chat with your data, chat with your dashboards, right? And so these companies are trying to bring Gen AI capabilities, but they're kind of these one-off add-ons to existing tools that are not really unified across your stack. And they kind of use different models and have different varying sources of quality. And the last thing, which most BI systems don't talk about, or tools, is that at the end of the day, you don't just get insights to your data and just sit there with them in your head. You have to take action on that data, right? And sometimes it's as simple as sending a Slack message, but sometimes it's creating a report. It is filing a ticket. It is taking some action that you think is going to resolve the issue. And so until you can kind of address this entire space, there's still going to be some painful bottlenecks that data teams have to deal with in trying to manage this structured data space that we're in right now. And so at NumberStation, our plan is to first first and foremost say you should keep your data where it is, right? We don't want you to have to transform all your data from one data warehouse to another. Our goal is to provide a unified kind of AI layer that lives on top of your data sources that we can learn from, right? So that starts with sort of our version of a unified knowledge layer. You can think of this as a giant smart index where we have learned from your data sources what is meaningful to you, what questions you kind of ask, how you ask questions. We have, which is, Madelon's talk was great about this, a huge retrieval layer on top of all this that has to go and search over all of your data assets. And then we're having this AI agent data layer, which the whole plan here and what we're building and have built is agents that are gonna go and perform tasks for you and take actions for you. So that means that we do have search agents that go and search over your different data assets. We have analytics agents that help run SQL queries for you and help do Python analytics for you. And then we have tool agents at the end that are gonna go and take actions for you. You know, again, even as simple as just sending a Slack message can save someone time. And so a quick, very high level example of what one of these sort of examples would look like. If a user kind of comes in and asks questions like, do we have any dashboards showing the Q3 2024 KPIs, which are, you know, commonly they'll have dashboards for each quarter or each year. You know, our search agent can go back and respond and say, hey, look, we have 2 dashboards. One of them is looking at Q3 of 2023, and another one is looking at, you know, marketing KPIs in general. The user can come back and give feedback, right? And that's a huge benefit of all these models is the ability for kind of having this interactive interface, which also goes back to Madelon's talk around search and how important that is. You know, and they can say, hey, look, you know, I really only want the finance, you know, OKRs for Q3. The analytics agent can come back, you know, understand that, you look, search isn't solving the problem. We're gonna have to go and potentially write a SQL query. Shows the user a dashboard, and you know at the very end they're like, oh, hey, look, send this on a Slack channel, right? This is a very high-level example. I'll give a much more concrete one later on. But you get the sense that, right, like our goal is not to remove the data analyst from the workflow. Our goal is to automate them as much as possible, and they're there to provide feedback and guide the process. But we want to make it so that instead of it taking weeks for them, it takes an hour to answer a question, or even minutes, ideally. Okay, so I'm now going to go a little bit more into the technical part of this talk, which is my favorite part, and talk a bit about what it means to build a structured data agent, and then what do I mean when I talk about these kind of multi-agent systems that work together. And so I'm going to actually go into a very classic example that a lot of people have seen before, which is text to SQL, and I'm basically going to frame it to you in an agent sort of agentic framework light to hopefully kind of understand how we're thinking about this in a very familiar problem space. And then I'll move on to a little bit more of how the multi-agent stuff works. And so again, and Till did a good job also sort of presenting some of the stuff, and I know, you know, DuckDB has done some cool work in this space as well. So the classic sort of text to SQL problem is you give the LLM a little information about your table and a question, sort of like how many customers do I have in California? So it's a pretty straightforward question. And this was one of the first examples that, like, I know OpenAI, the GPT-3 model that came out years ago now, that they were showing could be done. You send it to a model and it comes out with some SQL query that you can go and run, right? And this was pretty mind-blowing at the time, right? Text to SQL has been in the database community for decades. Now, the problem with this is that this is great, but it doesn't actually take action for the user, right? Like the user still has to go and, like, if you've ever used OpenAI to do this, you usually have to go and copy the query and enter it into some Snowflake UI and see what the result is. And so we really want, the first step here to kind of making something more agentic is to kind of give the models actions, give the model tool calls, if for those of you who are the engineers and familiar with that phrasing. And so here, we're going to now augment these models with tools, right? And in this very simple scenario, the tool is going to be something that literally just goes and runs a SQL query, right? And again, this is not a complex tool, but in general, tools can be anything that has a function signature. So an API, it can search the web, it can, anything that you want to code up can pretty much become a tool. And so in this case now, the model is going to output this, kind of tool variant of a SQL query, and we can actually go and run the result, right? So we're doing something that is now useful for the user. We are taking a little bit of action on their behalf to get an answer. Now, the problem obviously is that in this case, this isn't really an agentic platform. What this is just a model with a tool call, which is the first step. But the model, the core idea, for my opinion of agents, is it can actually make a decision based on an output and update its own state, right? You are not, from an engineering perspective, you are not building a monolithic control flow of what your agents are doing. You're kind of letting them do it themselves, which has like anyway, if you're curious later, I have a ton of thoughts on what this means for engineering teams going forward long term. But it kind of changes how you even think about building these systems. And so in this case, what we're going to do is really now make what we're calling an agent, a SQL agent. And so here it has the same old capability of generating SQL. It has this tool call, but now we're going to be able to route back to itself in order for it to really be this kind of agentic flow. So the first step, right, it's going to write SQL. It's going to be able to execute the SQL. We're going to feed that error back to the agent. It can now update the SQL to generate something that actually runs and gives us an answer. And you can kind of continually iterating in that sense. Now, this answer is still wrong, as I'll get to in a minute, but this is really the core insight about why agents are powerful. You know, I know this is a somewhat of a simple example, but you really need them to take actions on the output space to figure out and solve problems on their own. And this is kind of a global thing across many different tasks. Now, the problem with this, and I'll tie really nicely into Madelon's retrieval talk right here, is that for anybody who's tried to implement text-to-SQL over real enterprise data, is it never works, mainly because the calculations for computing something for enterprises don't match what OpenAI's best guess is. And so in this case, if you actually went and implemented some sort of retrieval layer over the semantics of what it means to be a business, their notion of what it means to be the number of customers isn't just the number of rows. It's usually some rows, in this case, filtered on the customer not being closed, right? And you will have, especially if you deal with structured data being fed into Tableau, they become these morphed structured data sets built for dashboarding, where you get these weird like filters that have to be shoved into aggregates for anything to make sense. And so it just means that standard OpenAI is really not going to be able to answer anything even remotely correctly from the metric sides of the world. And so going back to that knowledge layer that I mentioned earlier, all of this is kind of ingested and scraped from your Tableau workbooks, from your documentation, so you can retrieve from it on the fly and let the model understand this. And the beauty of these tool calls that I mentioned earlier is we can literally just shove retrieval as a tool call to the model so it can figure out when it needs to do what. And so typically what happens is these models get a question, and the first thing they do is retrieve over their schema to understand what the model what information's out there. It then is going to go and issue this kind of SQL tool call and run the SQL query. And in this case, it's finally going to get the right result for the number of customers because it's been able to see the information from their own metadata. And this obviously is iterated on. And so we've actually shown on, these are some sort of proprietary customer data sets, that you're looking at 20 plus points lift when you do this kind of RAG SQL tool call approach versus traditional text to SQL. And a lot of this is really tying it back to the semantics of what your data set is. Yeah, so it's valuable to have this full kind of end-to-end agent being able to take action, understand your data. Okay, so I'm now going to go into sort of this next step, which is these multi-agent systems that are the things I'm right now by far the most excited about, mainly because there have been moments in the last 3 to 4 years you're playing with something and you get that, oh wow, this is kind of magic feel. And I've had a couple of those moments in the last few months playing with these multi-agent systems, which is really fun. Anyway, and so here, the thing that, that first agent, the SQL agent that I talked about is great, right? Like it helps solve the SQL task. But for real data teams, they don't actually, they like that idea, they're not against it, but that doesn't actually solve their workflow, as when users come in with high-level questions, a lot of it starts with search. It requires new stuff to be generated in SQL queries. It requires, again, these actions to be taken at the end. And so you really need these kind of more complex multi-agent systems to be able to work and automate. And so in this case, we lean into this idea that, hey, look, I've just shown you how to build a SQL agent. You can actually build an agent that does all sorts of different things, right? And so a use case I'm going to walk through now is one where you have one that can generate SQL queries, one that can generate charts in Python, which actually, if you kind of give it structure around what you want to do, works pretty well. And then you can even have dedicated specific search agents around reports or specific data sets, right? Basically, some of the research Madelon's been doing, which we should talk about later. And what we're going to end up doing is allowing another agent to, in essence, route between all of these via, again, this idea between tool calls. So in essence, you build a global assistant that thinks it has tools that will magically go and, build a chart or build a SQL query, and you kind of build this hierarchy where agents can kind of collaborate and work together to solve a task. And so I'm going to walk through an actual example of what this is going to look like step by step here. Okay, so I'm changing my question a little bit to make it more relevant here, where a user comes in and says, hey, look, show me my customer churn in the United States versus Canada, right? They want this kind of comparison of a churn metric. And so the planner, who now thinks it has sort of gold models that can generate SQL queries, run a chart, and search, is going to go and first understand, hey, look, maybe this is already answered in the reports I have available. So it goes and routes to the search agent and says, hey, look, search for customer churn reports in our system. Now the search agent, and I'm kind of obfuscating the internal messages itself, will have different tool calls and this whole iterative agentic process to go figure it out. And it's going to return some result, trying to understand the reports that we have. And in this case, we're going to have a report that's looking specifically at Canadian customers, and one that's looking at overall kind of performance metrics across the globe. And it's going to respond that to the planner. And the planner here, again, after seeing this summary result, is sort of acting as a super intelligent user in this case, is going to understand, hey, look, the user still wants churn comparison. These reports don't have this. So in this case, I'm going to have to now go and generate something new, a new report, a new chart for the user that has these comparison metrics. And so in this case, it's now going to go and route to that SQL agent, have it generate a query that's looking at the churn in the United States and Canada. We'll get that result back and then feed it to the charting agent to go and generate a chart for you. And this is one of those things where, we were thinking about this workflow a few months ago, and I was a little skeptical that we could actually build something that worked like this. And if I had more time, I would show you a live demo that is doing something exactly like this, right? And to be fair, there is some brittleness and a lot of, things to work on, but it works. And in a way that was that kind of some moments of magic for me, that I was really able to route and do this on the fly ad hoc analysis, integrating the full end-to-end workflow here, which was very exciting. So I'm going to give folks a couple minutes for questions and to see if there's any hopefully give us a little time back. But anyway, so please come chat with me afterwards. There's a QR code. We have a bunch of blogs on this. The big takeaway here is there's something really exciting about these multi-agent structured data systems that we're gonna need a lot of good research coming in on how to do search and how to do all these things correctly. But this idea that they're really going to be able to address some of these pain points, but by building this kind of unified agent layer for structured data tasks. So thank you guys so much. I'm glad you guys are here. So any questions? I'm free. Yeah. Yeah, go for it. Or were you just stretching? Okay, great. Okay, I thought so.
So do you think some agents can actually do transforms, like the second talk was do small LLMs to create these semantic meaning inherent within the data? Do you see that as a
Yeah.
that you have or you could hook into literally what's in the tables connects on questions?
I mean, and at some point you have to start building kind of hierarchies of agents. But I actually did some research work a couple months ago before we productized this whole thing, building, I had this open source data agent platform where I did build AI little data transformations, right? Where the user could say generate this column that's sentiment analysis, right? So it does that well. The thing you have to be really careful with on data transforms is it gets very expensive very quickly. And so that's where small model training is really critical. All the stuff Till did around code generation, the emphasis, speed is great, but the money it saves, the data wrangling paper, you could not deploy that, right? It would cost you, especially with GPT-3 at that time, a ton of money. And so a lot of things you have to be a little careful in that space, but it can do it. Yeah, go for it.
Since you are sending the routes back to the planner agent,
Yeah.
you have a recursive problem, right? How many times, where would you stop?
Yeah, you have to be careful and put some guardrails in place because agents can get in these weird mind loops where they'll just kind of keep on iterating back and forth. The best solution we have, and this is actually there's a whole slew of very interesting problems on the UX for agent platforms because you get into this really interesting trade-off space where if if things ran fast enough, I would only show maybe the high-level messages to the user, but they're not. And at the moment, we don't want to trade quality yet. And so you kind of have to show the user a lot of what's going on and how the routing is handled. In this case, you can kind of say, hey, look, if it's spinning too much, we're going to cut it off and can route it back up to the user for feedback, right? So the user still has to be in the loop watching this whole thing happen to help prevent or at least figure out how to solve. Because, yeah, agents don't always get it 100% right.
You weren't certain this was gonna work, but you still give it a try. And so how many times numbers, try and errors do you face, and what you learn the most from those trials?
Yeah, no, that's a great question. And I think we started on this route about 6 months ago, doing some research and just seeing if there was something in the space, and then really being convinced a few months ago to put it in the product, which we've kind of released since then. Honestly, with all of these things, the most important thing is always the data quality. The schema and the data that's being fed to your model is usually 10x more important than the prompt. And cleaning that up, cleaning the messages up, cleaning what is seen to the model, like they might have infinite context, but like if, going back to the retrieval problem, there's enough red herrings that can get really confused. And so you have to be very careful with how you clean the data. Yeah, exactly. Yeah. Well, I will happily chat later. Anyway, thank you.
Yeah, we now will move to the break for networking, drinks, food is over there. Very nicely sponsored by MotherDuck. Thank you so much. And everyone is around, so please find us back in 20 minutes. Because we have heard about amazing performances, many good success stories, but of course there are also difficulties. And then the second part is interactivity.
Okay, that's fine. We can share.
Oh yeah.
Good.
So the second part is about interactivity. I think it's nice that we've seen lots of abstractions now, agents doing all kinds of stuff. But I think Bryan and Shreya might also chime in there in where the human comes in and where interactivity plays a role. And then I'd like also to open the floor to you for any remaining questions. So mainly starting on the challenges. I'm not going to sit down, so you can also just spread. Yeah, it gets very cozy here, but that's also nice. So maybe who wants to start with the challenges that you've seen? So what doesn't work? Is it data privacy? Is that really an issue? Or I guess at Kumo it isn't, but with structured data, this might actually be an issue. So any takes on challenges, or is this?
What is the question again? Sorry, can you?
So besides success stories, so you see many of them. Like, what are the challenges currently when deploying models for structured data in production? Is it adoption? Is it, generalizability across workloads? What's the data privacy?
I can make a start.
Yeah.
So I would interpret the question as, in our context or in the context of the talk that I gave, we're using, or the idea is to use large language models to help with data transformations or data preparation and to make that easier. And one of the challenges there is that language models are inherently not deterministic. So, and that's something that data engineers are actually very concerned about. So if they can write a regular expression that solves the problem, they would much rather do that than having a language model that solves it 98% of the cases because they're really worried about the 2%.
Yeah, so I think especially with LLMs now, the ratio of the number of people who want to use AI and machine learning to the number of people who are ML engineers or people who are trained to write code, use these models, leverage databases, even write SQL queries, right, is so large. And as a result, right, you're seeing all these people try to use tools and fail at using them. And it becomes very frustrating. I work a lot with no-code, low-code, but primarily no-code use cases. And I see a lot of people kind of take in some documentation on a tool, give it to ChatGPT, ask ChatGPT to write the code for them to, deploy on their Spark cluster or so forth, and something breaks, and then I get a message in a Discord for one of the open source projects that I've built, and I have to figure out why. It's pretty funny. This happened 3 times this week. And I don't know how we're going to solve this problem. I'm sure you get more than 3 of these messages at DuckDB. I'm sure you get millions of these messages at Kumo, but I'm super curious how we can really create an ecosystem of people who feel empowered to use tools without having experts always help them every step of the way.
Yeah, I can say a bit. So I think for us early on, security reviews always took a lot of time, but now with these kind of integrations, that's much faster. The other thing that Shreya was saying, I think is important, is like this human expertise and understanding your data is very, very important. And especially when you are doing these predictive tasks, right? Because the predictive task is never given to you. What is given to you is a business problem. It's like, let's lift this metric, let's increase the efficiency of our sales team. And then it's unclear what is actually a good predictive problem that will lift that. And you need to iterate a lot and quickly, and you need to have kind of accurate predictions that you're not able to put in productions, or where your downstream infrastructure is all buggy, or you don't have a robust A/B testing platform, makes things very, very hard.
I see. So, from this, on the same topic, I think Laurel, in a multi-agent, pipeline, how does this play a role for your side? Like having this transparency in what is happening, where failures come up. How do you deal with that then?
So I think something that is actually really important in this new Gen AI realm is the UX that you build on top of these structured data tasks, right? Because you need, unlike raw unstructured data, you need a lot of user knowledge that's baked in their heads and through years of training and passed down between data engineers, and you'll have scripts that were written a decade ago and no one knows why, but it magically works, you just can't touch it. And that knowledge has to come in from the user, and so you really need this perfect balance between user feedback and what the model can do. And here the goal is not to automate the user away. You just want to make them, okay, maybe eventually, but to start, you just want to make them more efficient. And so getting that right balance, and you actually have different personas that are all going to be interacting with your system. You'll have those who are data experts and they want to look at SQL and they want to make sure it's correct, and you'll have anywhere from analysts who don't even know what SQL looks like and they just want charts, right? And so actually understanding all your personas and making sure you kind of can interact with all of them is really important.
I heard one interesting point there, that in the future you do intend to abstract humans away.
I think.
Do you think it's possible? Or should it be the goal?
I certainly think it's an interesting goal. I think, why not? I think there is a lot, especially these models keep on getting better. I have a hard time imagining that we won't slowly eat at the space. I think you're always going to have some, if nothing else, just for some notions of trust, because you get a lot of people who are very ML skeptical, right? They've played with an AI system before, they got burned, and now they're fairly convinced nothing's going to work, right? So you're going to need a lot of, users to help make sure the performance, the model's behaving well enough and the quality is good enough. So I think it's going to kind of shift the roles in the company. But I think a lot of tasks can eventually be automated, but there's that trust and accuracy barrier that we kind of haven't crossed yet. But hopefully one day.
Fascinating. So Bryan, on your end, in terms of interactivity, do you align on this vision, or?
I think somewhat. So we've had agentic, automatic data analysis workflows in production since about a year ago. We've had thousands of users interact with Magic. I think what we've learned is that, to some of what you were saying, that very deep interaction patterns are really essential. We didn't invest initially in sort of rapid iteration loops. We invested more in more automation on the agent side. And what we learned is that users didn't really like that. Actually, users they kind of want to take little nibbles at the elephant. They want to make a very small step, and then another small step, and another, and another, and another. And so we introduced like diff-based editing, quite a while back, even before Cursor, and sort of like having these really, really fast feedback loops around user asks for something, we update in minimal amounts of diff what has changed, and then we allow them to rerun it. And we do kind of combine that with agentic workflows. I think the thing that I'm a little less certain on, I think, is the sort of dream of like large-scale automation in these workflows. One thing that I believed in last year that I'm less confident on now is that users kind of want to like ask a big hard question, come back and get an answer. And this is a little bit more close to like what Kumo is doing. Kumo, I feel like, is abstracting away one of the things that I think is like very difficult to abstract away. But I've become less convinced of that.
Which one? What are we abstracting that is hard to abstract?
Well, I mean, I kind of got out with my question about objectives, but like, yeah, I think this idea of like this ultimate, you're taking a very like limiting perspective on like holistic learning and kind of like there's one model that can learn everything simultaneously, which I think is impressive and I'm very curious about, but. It feels like the bitter lesson, but like the maximal version of the bitter lesson. You're not just like one model can learn everything. You're like one model can also do all the feature engineering too.
I mean, if I may respond, right? Like I think what we are doing is just like old school supervised learning.
Sure.
Right? Where it's not that one model needs to be able to recommend and do fraud and predict the accidents and everything else, right? It's a model that's kind of fine-tuned for one specific task. And we see these models, like if you say, okay, how data hungry are you? We can do fraud with few hundred, less than 1,000 examples. And for food ordering or clicks and things like that, we have billions of those. So the models kind of nicely scale on this from kind of small data to big data. But these are just supervised models fine-tuned for a specific task through that training table and the objective function that data scientists can specify. So I think the data scientist and their role is like super important, and this is just kind of a tool that allows them to focus on modeling and do their work. Another thing, that is important is how do you shape your data, right? Like how do you organize it into tables? How are these tables connected? Because that determines how kind of the information flows through that graph. Perfect. So that becomes interesting. So human for us is very essential.
Great. That's actually super helpful in terms of understanding. When you were giving your talk, I was a little bit uncertain on sort of if you ask it to also try to learn the links, and it sounds like building the links is pretty important.
Yeah, that's we let the person who knows their data tell us what is linked how. I mean, we try to infer kind of on column names and things like that, but at the end, it's the human who says, this is how I want to do it.
Okay. It's feeling a lot more harmonious to some of your previous work now. Now I think I'm getting it a little bit more. But
that's already a great outcome. So Shreya, from your perspective, I know you've been like researching HCI principles. How do you think human-computer interaction, where should it like come in terms of gaining trust in these systems? What's happening there?
Yeah, I think it's such an exciting time for HCI. I got into HCI because I thought it was an exciting time for HCI, so maybe I'm biased. But I agree with Bryan's take on people want to iterate on workflows, especially in this AI world where it's not like traditional data processing or like relational data processing where you write a SQL query and your query is going to have a correct answer. Like you can't assume that anymore. The answer is not going to be correct. And you're now just trying to build, as a human writing this, you're trying to build a mental model of the incorrectness here. And that requires iteration, especially when operators are machine learning powered. You never know what, we have a paper at WIS next week, but the core finding is that you don't know what your query or your operation is going to be until you see the result of that the operations output. There's a catch-22 there that requires iteration. And this is dependent on your query plan. This is dependent on what your validation criteria is. This is dependent on pretty much the entire life cycle around it, which I think is interesting. And I think it also plays out in a lot of our research. We try to optimize for accuracy. We do all these expensive workflows to boost accuracy or make something maybe more efficient in the long term. But if you do that a little bit too prematurely before the user has even figured out what they want to specify, then you risk losing them. And that means like in your initial exploratory stages, like how do you build like low latency query processing systems that allow users to move towards their goal of what the task is, what their query is, and then we leverage pull out our big guns and do optimization there. And I think that's like a very interesting HCI problem to explore.
Cool. Anycam, I see.
Yeah, no, I have one thing to add though, which is actually going back to what Till said earlier about the fact that these models aren't deterministic. And that's actually something that I find, like a little bit of my motto from an engineering side is that if you find that you're fighting the models a lot, you're probably like thinking about the problem a little bit wrong, right? And the issue is like in a structured data world, everyone is expecting determinism. And I think the goal should be do not give them the promise of deterministic outputs, but build an experience and like an interaction framework where they are comfortable with the fact that it will be non-deterministic. And a lot of that has to come in with user feedback, like chat, incremental updates, like that is one of the most important things to getting like to fixing some of those issues, because these models are not like, they're not built that way, and we shouldn't treat them that way. It's just really hard to get things to work if you do.
One comment about it. It's related to work that you have been working on, Shreya, on comparing basically machine learning models and their output to crowdsourcing or crowd workers. And I find that really, really interesting analogy, and I think, yeah, it's an interesting way to think about the uncertainty, to think, okay, if humans are involved in the process, there's also uncertainty there. So it's also a fallacy to think about data in a database as being correct and accurate. As soon as the human has been in the loop at some point, it might be subject to very similar errors that a language model would do in the same context. So I'm wondering if you have any insights, like from that perspective, on this topic.
Yeah, that's a good point. And I don't think non-determinism is a problem. Like, we know how to deal with non-determinism when we work with humans. What's the problem is when your mental model of their errors and their successes, you can't fit a mental model to that. I don't know if that makes any sense, but you have to be able to kind of model the accuracy or be able to understand what's a decision someone might make or some LLM might make if I give it a prompt. And I think that is the real parallel with crowdsourcing. There's an interesting paper called Why Johnny Can't Prompt, great name, by J.D. Zamfrescu-Pereira at Berkeley. And he ran a study with a bunch of people who had never seen AI machine learning before, asking them to write a chatbot. And this was on top of GPT-3.5 Turbo or GPT-4, I don't remember which one. But he found that all of the participants got frustrated because they expected the AI to make the same mistakes as a human and make the same successes or correct answers as a human. And once the AI violated this model of the low code, no code domain expert, then they were done with the LLM. So I think that has parallels in a lot of different areas.
Isn't there potentially hope that these things are going away over time as language models get better? And I mean, in the end, they're trained on data that is produced by humans, and I feel like they're, over time, probably converging towards just, being exactly like someone who has written a text that they've been trained on. Who knows?
Okay. Do you want to comment? No? Okay. I think it's time for also some questions from the audience. Can I get one microphone? Okay, thank you. All right. I think we can take 3 questions maybe.
Yeah, I'll be quick. So, question for you, Kumo. Jure. Apologize. So it's very interesting, right, that you're sort of saying that structured data can be kind of like completely unstructured, use neural networks and so on. But don't you lose what a lot of people have been saying, the deterministic? Would you replace your SEC filing with a structured data that will use your process to determine how much money you made in a month? Because otherwise, the SEC will fine you if you don't get the accurate sales information. Would you do that?
I would say I can. So you are talking about running queries over the past.
Yes.
These guys do that amazingly well. What I'm doing is I'm running queries over the future that hasn't yet happened. I will predict how much revenue you will have next quarter or next year. That's what I'm doing. He's doing telling you how much you made last week.
Answer. Okay, perfect. And then last question for you is, what happens when the structured data changes? Do I have to retrain my model again and restart from scratch? Because basically the weights are no longer valid.
You mean if you change your schema?
Exactly, because that happens all the time.
Yeah, you can retrain. It's no problem. Retraining these models takes a couple of hours. So this is not weeks on 10,000.
But your forecasts are completely wrong.
Sorry?
The forecasts that you made with the previous model are completely wrong.
Well, why would they be wrong?
Because now you have to have a new model and reforecast again. So whatever you said to people could be completely different to what the new model would say.
I updated my forecast, yeah. Yeah. I mean, of course. But I think the beautiful thing here is like when, for example, you see this in fraud detection all the time. People change their behavior to kind of try to circumvent whatever defenses you put up. So when you do feature engineering, you are always behind. Your model is deteriorating and you're like, okay, what do I do? Oh, I engineer more features, I retrain. Oh, it looks good again. 2 weeks later, it's starting to tank. You need to engineer more features, retrain the model. So in industry, you are retraining the models all the time. Right? The beauty of our approach is just refresh the data, retrain, and the model will learn the new signal that's in the data. Whatever the fraudsters are doing, the neural network is going to figure that out. So it's the model retraining. You want to be doing that every week, every 2 weeks, whatever. So that's okay.
Can I ask a follow-up to his question?
Yeah.
Sorry, there's a mic right here.
Oh, sorry.
I just want to ask a quick
Let's first do the follow-up. Yeah.
So my question is, do you do your revenue forecasting for Kumo, with Kumo, for your board?
No, that's a great question, right? So when we actually, let me answer that. So when we started the company, we were like, this will be amazing for data analysts, right? They will just be able to do AI. They will stand in line for 7 hours to use Kumo, right? Didn't happen, right? No, so I think the point, right, is like, so the point is, when you are making a single prediction, like what will be our revenue next quarter, that's more art than a science, right? So I wouldn't use a neural network to do that, right? But if I am, recommending restaurants to 200 million of my users, then when I will be using a neural network. Or when I'm, predicting risk scores, that's when I'm using my neural network, right? So kind of, our conclusion was that the data analyst is kind of not able to consume these predictions. Who consumes predictions is machine learning engineers, data scientists, and developers who want to push this out through their applications to the end user. So that's a great point.
So for students, let's say in Berkeley or Stanford learning computer science, there's old school concepts like your structured, relational data, all these new concepts here. What are the new skills you would recommend for young students, new students here to actually take advantage? Like if you had to do like a, databases 101 revised course for the future. Open question to anybody.
So I work mostly on problems that are actually sort of in the negative space of what Jure was talking about. So the problems that wouldn't be great for Kumo based on what he was saying. So a lot of problems that involve a lot of art and science. One thing that came up in your talk was about sort of like data quality and schema quality. And that's the one thing that I've seen across my career as a data scientist, which is the more time that your data engineering and analytics engineering and data analyst team puts into really great like schema quality, the benefits are like really outsized. And not just for LLMs, that's very obviously true, but it's incredibly true for anyone trying to work with that data. So I think it's a very boring answer that I tell my students actually, which is that like data engineering is much more about trying to make it intuitive how the data looks and works together as it is about like computing different columns or feature engineering or anything like that. Data engineering is much more about like writing. That's on the pure data like architecture side. I think the thing that I tell my students on the sort of like working with data and doing inference and sort of like building models, I think, and this is where we came up a little bit before, but like I think the most important thing that we should all be paying attention to is problem framing. Problem framing, I think, is the thing that will remain human as we move forward into this new era. I think data framing is very important. And I think almost all of the technical components are going to get less and less relevant. And so problem framing is like the one main thing that I care about and push my students really hard on.
Shreya, did you want to add something to that at first? No? Laurel?
Okay, I have another small thing here, which is like if there was a single thing I would teach ML engineers or anybody going forward, it is like it's really easy to be caught into this loop of you're trying to get a model to work or training a model and you just keep on throwing hyperparameters at the problem. Like you just train, trying to fix the problem, right? You will learn so much more by pausing and like looking at the data, the input data, the training data, the evaluation data, and like it is dirty work. Like it is not fun and it will take you a couple hours to understand what the model is doing, but it pays off 100-fold. And so like every time I'm interviewing an ML engineer, like I ask them their process. And if they don't talk to me about that, like, you know, and to be fair, ML has been in a magical phase where like throwing hyperparameters kind of worked for a while. And so like people, you know, learn these habits of just like, like I'll just train all these models, and like it worked. And I don't know, I mean, kudos if it keeps on working, but like, you know, you're just a lot more efficient if you actually look at what's going on.
Can I like request that you respond to that? Because I'm curious in your world, you're like almost like the anti-look at your data. And so I wanna understand your perspective here.
Unless you look at it for you.
So
I didn't get that from the talk. I didn't get that you were anti.
What?
I'm torturing him.
I took his class. All I learned to do was look at my data.
I'm all about looking into the data. What I'm saying, I don't know, is like, right, like look at all your data and learn from all your data, not from arbitrary statistics that your biological neural network hallucinated and you thought you are an expert. But, you know, frame the problem, I think at the higher level, right?
Are you using autoencoders to self-learn?
No, we ask you to tell us what you want to learn, right, as a user. I generate the training data from kind of your instructions, what you'd like me to learn. Yeah. Yeah, no.
So based off of the research paper, do you have any open source?
So what we've done is we have a small kind of open source library plus a bunch of databases, actually tabular data sets, right? So it's actually interesting, right? People today will talk, like a lot of people talk about tabular machine learning and so on, but that means learning from a single table. And nobody has data in a single table. And if you have data in a single table, then use XGBoost and life is good, right? But if you don't, and everyone doesn't have data in a single table, then you are kind of doomed with this feature engineering. And Kumo kind of allows you to learn, or this relational deep learning approach allows you to learn over multiple tables, however they are connected. So what we did at Stanford is we developed a small prototype that allows people to try this out. We released a bunch of different tabular or multi-tabular relational data sets together with predictive tasks so that people can now start doing research on this and kind of improving the power of these models. So we have a small kind of academic prototype.
One final question, I think, and then we want to wrap up. I think between you two, You're persistent. Okay, let's go. Yeah.
Thank you, panelists. My question is directly to is Jure or Yuri?
Yuri. Yeah.
Yuri, okay.
Call me Kumo.
I wouldn't go that far, yeah. But thank you so much for the insight. My question, you mentioned that you can do the analytics work without moving the data, right? I mean, whether it's at Snowflake or Databricks. Do you assume those data are stored on Iceberg, or well, how does it work? Is that
so
the first question? The second question is, you mentioned the existing graph database doesn't really work, like Neo4j. Apologize, Alex. What is the you using that for a single machine? You said you never seen a real production case without being able to handle by a single node machine. What's the maximum data size? Is it terabytes, like 2 terabytes, or 5 terabytes, or 10 terabytes? If you don't mind.
Yeah, there were, I think. Thank you for your questions. Maybe you had 2 questions. The second one was data size, and the first question was about efficiency of where the data lives. Yeah. Oh, so the way this works is actually both, but especially Snowflake basically has a concept of an application that runs inside their data warehouse. So basically what our platform is like an application that runs inside your Snowflake account on Snowflake provisioned hardware, totally kind of isolated from the rest of the world. So your data never leaves the Snowflake, right? It's kind of almost like this iPhone model, right? I have an iPhone, I trust Apple, whatever is on Apple Store, I know is safe to install. So Snowflake has something similar where basically they have a set of applications and you can just install, and it installs on Snowflake provisioned hardware inside your Snowflake environment. That's why data never leaves Snowflake. And because we operate directly on top of relational tables, we learn from the tables, and our results are just a new table. So you can write very kind of complex machine learning kind of workflows that have multiple models kind of together by just reading tables, writing tables, reading tables, writing tables. Kind of the same way as you do this kind of historic data analytics, you are now basically doing predictive analytics with kind of different queries. And then in terms of scale, I think we scale up to 50 billion rows total right now with a kind of single, to have a large memory machine it's still a distributed system, but we don't distribute the graph. We distribute everything else, only not the graph. And there's a tons of cool stuff you can do because you actually know the schema. Tables are usually, it's not that all tables are the same size, some are small. So actually distributing these kinds of graph, I think, is much easier than thinking about distributing a social network or something like that. Those look like an onion, and I can explain what I mean by that.
Maybe we can move that offline because we're really close to the end of this entire meetup, and I want to give everyone the opportunity to chat a little bit for like 10 minutes or so. But first I want to thank the great speakers and panelists. Thank you so much. Also to MotherDuck, of course, for sponsoring food and drinks, and WeWork, of course, for hosting us here. It was a great event, and thank you to all for your interactions. Handing to Ryan.
And everyone thank Madelon as well for doing all the hard work and planning this. She deserves a huge round of applause.